Okay, so let's get started with a couple simple examples, and then we'll look at the more complicated examples with those different axes. Okay, so example number 1, we have y equals x squared about the x-axis. Okay, so we're given the bounding curves. So if we sketch all of this, we'll see that there's some region that is enclosed by all of these curves. Once we have that region, we need to imagine rotating it around the x-axis. Okay, then we get our 3D shape, and once we have our 3D shape, we have an idea of what we need to do for the integral. So let's sketch this. Okay, so y equals x, that's easy, it's just a line like that. Y equals x squared, that's going to be something like that. And we know that they intersect each other first at the origin, and then second at the point 1, 1. So at the origin, and then at the point 1, 1. So here we can shade in the region. Okay, please, in the quizzes and assessments and so on, please shade in the region so I know what you're working with. If you just draw the curves and no region, I don't know what you're working with. Okay, so please make it clear where the region is. And then once you make it clear, it's very easy to see what the volume would be. Because if we rotate this around the x-axis, like that, we can see that the straight line will form the outer part of whatever shape it is. And then the parabola part, that will be the inside part. Okay, because we're going around the x-axis. So the curve that's further away from the x-axis, that's going to end up being the outer part. Okay, so it's going to end up being something like this. Okay, so the straight line gives us this cone shape, but we also have the parabola that's on the inside. So it's going to look something like this. Okay, and then on the inside, we can put our hidden detail lines like that. Okay. So between the solid line and the dashed line there, that's solid, that's part of the volume. Everything else on the inside bit, that's hollow. So this region here, this open region there, that forms the hollow region inside our volume. So inside here, that's hollow. Okay, so the red part, that makes the solid part of the region. We can sketch that in here. So this red part here, that's going to be the solid part. The inside bit there, that's going to be hollow. That's not part of the volume. Since we've got a solid part and a hollow part, we know that we need to use the washer method. If we use the disk method, that's for solid shapes with no inside part, it's solid. Here we've got a solid part and a hollow part. We're going to have to use the washer method. Okay, to use the washer method, we need the outer radius of the washer and the inner radius. So we've got the x-axis. From the x-axis to the straight line, that's going to be the outer radius because it's on the outside of the curve. And then from the x-axis to the parabola, that's going to be the inside radius. So here, if we look at our axis going through here, from the axis to the outside of the shape, that's the outer radius. From the axis to the inside of the shape, that's the inner radius. And we can see the outside, that's going to be the line. The inside, that's going to be the parabola. Okay, so R in, that's going to be the parabola, x squared. R out, that's going to just be x. Okay, and that's what you need to do before setting up the integral. What's the inner radius? What's the outer radius? Okay, so what's the volume going to be? It's going to be the integral from 0 to 1, because that's our x limits there. It's going to be pi. Then how do we find the area, the surface area of the washer? It's going to be the outer area, R out squared, minus the inner area, R in squared with the pi attached. R out squared minus R in squared dx. So the stuff inside the integral, that's like the area of the washer. You times it by dx, you get the volume of the washer. Adding all of that up, you get the total volume. So here the volume is going to be pi, integral from 0 to 1. R out squared, that's going to be x squared. R in squared, that's going to be x squared squared again, so x to the 4 dx. Okay, so once you've set up all your integrals, then this just becomes a normal problem that we've covered before. Okay, so all the stuff about volumes and inner radius, outer radius, that's all of the pre-working step. Once you get to the integral, it's normal integration methods. Okay, so here it's going to be pi 1/3 x cubed minus 1/5 x to the 5 from 0 to 1. Okay, we can forget about the 0, that's not going to make a difference. We get 1/3 minus 1/5. A little bit of cross multiplying. So get the 5 minus the 3, so that's 2/15. Okay, and again, you can put units cubed since it's a volume, but I'm not worried about that. Okay, but just a warning, later engineering modules that you do, if you're trying to find the volume of something, maybe it's specifically centimeters cubed or meters cubed or something. In those modules, you might have to put the units. Okay, but for maths, I'm not worried. You can put it, don't put it. As long as you get this number correct, I'm happy. Okay, any questions on this one? Okay, so very similar to what we covered before the holidays. Okay, let's look at something else, a little bit more difficult, but not so bad. So number 2, we have y equals cos x, y equals sin x, x equals 0, x equals pi over 4. So those are all the curves that are going to form the region. And again, once you have the region, you rotate it around, and then that's your volume. Okay, and this is going to be about the x-axis. Okay, so once we got the region, we must imagine rotating it around the x-axis. Okay, so let's sketch this, see what we get. So y equals cos x, that's going to be something like that. Sin x, that's going to be something like that. Between x equals 0 and pi over 4, so that's going to be from the y-axis up to and including that first intersection point here. So you can put a dotted line there. So it's all of this here. Okay, right? Because at pi over 4, we know that sine and cosine are equal. So it must be up to that first intersection point. Everything after that intersection point, we're not interested in. So the region we're interested in is just the red part over there. The rest of it, you don't shade in. We're not interested in that. Okay, and this is being rotated around the x-axis. Okay, so what's this going to look like as a volume? Okay, well, we can look at the outside part first. Okay, it's a little arc bit that's being rotated around. So that's going to form this kind of shape. Okay, something like this. Okay, just rotate it around, you end up with something like that. And then the inside bit, we can put with hidden detail, it will be something like that. Okay, so the outside bit, that solid line, that comes from the cos graph on the outside. And then that hidden detail line inside, that's going to come from the sine graph. So here, all of this bit, that's solid, that's in red. That's in red. And then that space below the sine graph, that's empty. So in our volume, the space inside here will also be empty. Okay, so it's only this red part that's going to end up being solid. Okay, quite similar to what we had before. So the outside part, that's solid there. And then the empty bit inside is due to this bit here. So this bit here is unshaded, so in the volume it will then be empty. This bit here is shaded, so in the volume that will be solid. Whatever shaded here becomes solid there, whatever is unshaded here becomes hollow over there. Okay, so we've got this, and we know from the volume now, we're going to have a solid part and an empty part, so we have to use the washer method. So what do we need for the washer method? we need an outside radius and an inside radius. And those are measured from the x-axis, because that's the axis of rotation. So from the axis up to the cos graph, that's going to be the outside radius. So from the axis to the cos graph, that's going to be the outside radius, because it's the furthest away from the axis. From the axis to the sine graph, that's going to be the inside radius, because that's closer to the axis. So this is R in. Okay. And that's all we need for the setup. We've got the inside radius, we've got the outside radius. We can now find the volume. So the volume, that's going to be the integral from 0 to pi over 4. Those are our x bounds that we found from sketching. Then we have the pi, r out squared minus r in squared. With the pi, that gives us the area of the washer, and then we need to multiply by dx. That's the thickness of the washer, and that will then give us the volume. Okay, r out, that's going to be up to the cos graph, so it's going to be cos squared, and the inside is sine squared. Okay, and now this is just a trig integral. Okay, we forget about all the stuff about volumes. We just treat it like a normal integral and use whatever methods that we need. Here you could integrate both of them separately if you wanted to do that, or you could use a trig identity. This is just integral from 0 to pi over 4. This is just cos 2x. Okay, you could do it separately, or you could combine them into cos 2x. Whatever you see, right? There's many ways of answering these questions. Okay, so that's going to be pi over 2, and then we have sine 2x from 0 to pi over 4. The 0 doesn't do anything, it will just be 0. Sine of pi over 2, that's 1. So we just end up with pi over 2 units cubed. All right. Any questions on this one? No questions. Okay, again, once you've got your sketch, the outer radius will be whatever's furthest from your axis of rotation, and the inner radius, that will be the one closer to the axis. Okay, please keep that in mind, because when we start changing the axis, we need to be careful about how we measure these inner radii and outer radii. Okay, for these types of problems, it's pretty obvious from the x-axis. Now, if we change the axis, it gets a bit more tricky. Okay, we'll see that in this one here. Okay, number 3. So we have y equals root x, y equals 2 minus x, y equals a half. About the x-axis. Okay, so here, a bit more complicated. We just need to be careful about what's going to be the inside radius and the outside radius. Okay, so let's sketch this. Okay, root x, that's easy. It's just going to look something like that. 2 minus x, just a straight line with the negative gradient. It's going to be something like that. Y equals a half, they'll be over there. So this point here, that will be at 1, 1. Okay, and then that's 0, that's 2. Okay, so quickly just sketching this. The region that we're interested in is going to be enclosed by all the curves. So that's going to be this region here. Okay, we can see that the root function on the left, that encloses it. We've got the line on the right, and the line y equals 1/2 underneath. So we see that if we include all of those curves, it's going to be that red part. Okay, nothing else is included. Okay, so only this red part is the region of interest. None of those other spaces over there. Okay, and we're rotating this around the x-axis again. Okay, so now we need to be careful about what we choose to be the inside radius and the outside radius. Why? We see here this line y equals a half going all the way along here. That's going to be the inside radius. If we rotate this around, this is going to be closest to the line here, so that's going to be our inside radius. This root function is going to be the outside radius, but only up to this point. You see, from here to here, this root function is the outer radius. From here to here, the line is now the outer radius. Does everyone see how it changes? Okay, so from here to here, that's going to be, this will be the inner radius, this will be the outer radius. From this point to this point, this will still be the inner radius, but now this will be the outer radius. It changes as we go across. Okay, and we need to keep that in mind. When we do the integral, we're going to have the first bit for the root function being the outer radius, plus a second bit where the line is now the outer radius. We can't do it all in one because the radius changes as we go across. Okay, and then this over here, we need to find that point, and we need to find that point there. Okay, so how do we find the first one? We know that the y value is a half. Along this whole line, the y value is a half. This function is root x. Root x. So if the y value is a half, we have 1/2 equals root x. So x equals a quarter. So our starting point over there, with the dotted line, that's going to be a quarter. So the first volume we need to find will be from 1/4 to 1. Then the next volume we need to find will be from 1 up to that next intersection point. What's that going to be? Again, this y value is a half, so we're going to have 1/2 equals, but now we're working with the straight line. And the line was given as 2 minus x. So we have x is equal to 2 minus a half. So x is equal to, we can make that 4/2 minus a half, so that'll be 3/2. Okay, so that is 3/2 there. Okay, so again, the first volume is for the first bit. That's going to be from 1/4 to 1, with the inner radius being a half and the outer radius being root x. So let's put that for number 1. We're going from 1/4 to 1. R in is a half. R out is root x. Okay, so that's for the first bit of the volume. For the second bit, we're now going from 1 to 3/2. So for the second part, it's going to be from 1 to 3/2. And now the outer radius changes. R in will still be a half. That doesn't change. But R out will now be the 2 minus x, that line there. Okay. So we know what that's going to be. Let's quickly sketch what this will be before we do the calculation. So the R in is constant along there, so that's going to end up being like a cylinder. And then the outside part is going to be determined by that root x and the line. So it will be something like this. So root x there, and then a straight line. That's going to be the inside part of the cylinder. Okay, and then we have root x, and then a line like that. Okay, so it will be something like that. So you've got the cylinder running through the middle because of the fixed line y equals a half. Then the left-hand side of the shape, that's determined by the root function being on the outside. And then the right-hand side of the shape, that's just going to be like a straight line sides. Yeah. Okay, again, your sketches don't need to be pretty. It just needs to be a rough idea so you can see what's going on. Okay, and then the axis of rotation, that goes down the middle there. Okay, so it'll look something like that. Okay, so let's find the volume. So the volume is going to be the integral from 1/4 to 1 for the first bit of the shape. And then we have pi outer radius squared minus inner radius squared. So that's going to be x minus a quarter, plus the integral from 1 to 3 over 2 pi. Now we have the outer radius squared being 2 minus x, and the inner radius squared, that's going to be a quarter still. Okay, so now we can expand that right integral there and then just solve it as normal. So that'll be pi integral from 1/4 to 1, x minus a quarter, plus pi integral from 1 to 3 over 2. Here we're going to have 4 minus 2x plus x squared minus a quarter. Okay, and then we can do the normal integration from there. So that will be pi 1/2 x squared minus a quarter x from 1/4 to 1 plus pi 4x minus x squared plus a third x cubed minus a quarter x from 1 to 3 over 2. Okay, and then once you've substituted upper and lower bounds, you get your answer. Okay, you can just use your calculator for that. Okay, any questions on this problem? Okay, so everyone understands why we had to split it into 2 different volumes. Okay, let's have a look at the next one. Okay, so for this next one, we're not going to be rotating around the x-axis or y-axis. We're going to rotate around the line y equals 4. So whatever we had before, it will be very similar, but we just need to rethink what the inner radius and outer radius will have to be. Okay, so number 4, we have y equals x squared minus 2x, y equals x, about y equals 4. So that is our new axis. It's no longer the x-axis or y-axis, it's something different now. Okay, so how does this work? Well, let's sketch this. Okay, so x squared minus 2x, that's going to look something like this. Okay, here's 0, there's 2. Okay, y equals x, that's going to look something like that. And then they intersect here at 3. Okay, so this is our region, that bit there in red, okay, because the line and the parabola, between those intersection points, we have that red region there. Okay, so we're going to take this region and then rotate it around the line y equals 4. So not the x-axis or y-axis, we've got a new axis now. So let's put that in blue. So this line over here, y equals 4, we're going to rotate around that line now. Okay, but same idea, we're taking a region and we're rotating it around a line. Okay, so same idea, it's just now that the line has moved away from the axis. Okay, but same thing applies. We need to find the inner radius, we need to find the outer radius, and then we can set up the integral. Okay, but now the radius is measured from the line y equals 4, not the x-axis. So here, when we're finding the radius, it's going to be from here to here for the inner radius. So from the axis to this line is now the inner radius. From the axis to the parabola is now the outer radius. Okay. We're measuring from the blue line, not the axis anymore. Okay, so it's going to end up being something like this. Okay, so from the axis to the first line there, so we're looking from the axis outwards. So from the axis to the line, that's going to now be the inner radius. From the axis to the parabola, that's going to now be the outer radius. Okay, it's always from the axis to the curve. Like before, we went from the x-axis to the curve. Now we're going from the line y equals 4. to the curve. Okay, so how do we measure what these distances should be? Well, we know the distance from the blue line to the x-axis must be 4. That's given. So the green distance for r in will then be 4 minus x. Because this distance here, this distance there is x. Why? Because the line is y equals x. The y value is whatever the x value is. So that height y is just x. The whole distance is 4, so Rn is 4 minus x. So Rn is 4 minus x. Does everyone see that? Okay, I'll take your silence as yes. Okay, what about R out? It's going to be the same thing. That distance from the blue line to the x-axis, that's 4 still. What about the parabola distance? What's the height of the parabola? That's going to be x squared minus 2x. So if you know the full distance is 4, and the parabola distance is x squared minus 2x, then that leftover bit, the r out, is going to be 4 minus the height of the parabola. So r out is going to be the full distance 4 minus the height of the parabola, so minus x squared minus 2x. Okay, everyone see that? Okay. Now remember, this is just r in and r out. We still need to square it when we do the integral. Okay, what's this going to look like as a volume? Let's just re-sketch this here. So we got our axis over there. We're going to take this region and rotate it around. So let's just re-sketch the region at the bottom and then flip it over to the top, and then we'll have an idea. So it's going to look something like this. For the bottom part. So I've just redrawn the red bits over there. Okay, and it's being rotated around. So the top bit is just going to be the mirror image. So it's going to be something like this. Like that. Okay, so I've just flipped it over there. Okay, and then it's just going to be something like that. Okay, and then this bit, there should have been hidden detail there, so let's just fix that. Okay, so it ends up being something like that. So it's like a cone shape, but then the outer walls we've just made thicker because of the parabola part. So the inside bit with the line, that's just like a normal cone, but that parabola bit makes the walls a bit thicker because of that region here. So we can put that in red. So this bit here and this bit here, that corresponds to that bit between the line and the parabola, making the walls of that shape. Okay, and again, this inside part, that's going to be hollow or empty. All right. Okay, and that hollow part, that empty part there, is the space between the blue line and the line y equals x. Okay, that part wasn't shaded in, so it ends up being hollow for the volume. The space between the line and the parabola, we shaded that red, so that ends up being the solid parts of that shape. Okay, let's find the volume. So the volume is going to be the integral. It will be from 0 to 3 because those are the intercept points. They intersect each other at 0 and they intersect each other at 3. So those are the endpoints we need. So it's going to be pi r out squared, so all of that squared. Okay, so everything inside there that needs to be squared. Minus r in squared, so that's going to be minus 4 minus x squared. Okay. Everyone okay with how we set up the integral? Okay. So this is going to be pi integral from 0 to 3. We can expand that first bit out. So that's going to be 16 minus 8 x squared minus 2x plus x squared minus 2x squared. Okay, so that's just expanding out the first bit. We can expand out the second part there. So that's going to be 16 minus 8x plus x squared dx. Okay, let's just expand the bracket with the minus 8, and then we still need to square that second bracket there. So that's going to be pi integral from 0 to 3, 16 minus 8x squared plus 16x plus, then we can expand this out now. So that's going to be x to the 4 minus 4x cubed plus 4x squared. Okay, and then the last bracket, we just put a minus sign in front of everything. So that's minus 16 plus 8x minus x squared. Okay, quite a few things cancel. We've got a plus 16 and a minus 16. That's going to go away. Okay, we've got x to the 4. Let's put that in the front. So the integral is 0 to 3, x to the 4. We've got the x cubed there. Let's put that here. Okay, plus 16, plus 16x there. So let's put the squares first. So we've got minus 8x squared. Okay, plus 4x squared. We've got another minus x squared. Okay, and then we've got the 16x there and 8x. Okay, so that's just organizing everything there. We can group some things together and then do the integral. So it's going to be pi integral from 0 to 3, x to the 4 minus 4x cubed minus 8x squared plus 4x squared. That's going to be minus 4x squared minus another x squared. That's going to be minus 5x squared. 16 plus 8, that will be plus 24x. Okay, now it's just a normal polynomial. Okay, so just use the power rule for that. So that's going to be pi 1/5 x to the 5 minus x to the 4 minus 5 over 3 x cubed plus 12x squared from 0 to 3. Okay, substituting 0, that's not going to do anything, so we can just put in 3. So that will be pi 1/5 3 to the 5 minus 3 to the 4 minus 5 over 3 3 cubed plus 12 3 squared. Now you can just put that in your calculator to get the final answer. Okay, any questions on this one? No questions. Okay, so again, if we have a different axis of rotation, the R in and the R out must be measured from the axis. So from the axis to the line y equals x, that's going to be R in. From the axis to the parabola, that's R out. Okay, your R in and R out is always measured from the axis, whatever it might be. Okay, any questions before we move on? Okay, just a note for your June exam. This disc method, washer method, shell method, this will be 30% of your exam. Okay, so that will be the 30%. The other 30%, that will be your integration methods. So U substitution, partial fractions, integration by parts, trig integrals, all of that stuff. That will be another 30%. And then the rest of it will be other applications of integrations that we're going to be looking at, and some other stuff, improper integrals and all those other things. Okay, but disk method 10%, washer method 10%, shell method 10%. So if you don't understand this now, you're missing out on 10% for the exam. So again, are there any questions on this before we move on? Yes. Oh, sorry. Sorry, I can't hear with the noise. Repeat question 3. Okay, so let's go back to question 3. Okay, so here we had y equals root x, y equals 2 minus x, y equals a half, about the x-axis. Okay, so we need to sketch this first and then see what we need to do. So sketching this, y equals root x, that's going to look like that. Y equals 2 minus x, that's going to look like that. Over here, this is going to be 1, 1. Here, that's just going to be 2. Okay, so that's just sketching that. We also need to sketch y equals a half. That's going to be here. Okay, so the intersection of all of those curves, that's going to be the region of interest. That's going to be this part over here. Okay, that bit in red. So that red part is what we need to rotate around the x-axis. Yes? Sorry? The intersection. Yeah, no, because root of 1 is 1 and 2 minus 1 is 1. So that's the intersection. If you don't see it immediately, you're going to have to do the calculation on the side. Okay. So if you don't see how you find the intersection point, root x equals 2 minus x, solve for x. Okay, or you could just see that root 1 is 1 and 2 minus 1 is 1. Okay. And then the same thing here. That was a quarter, and this was 3 over 2 by the calculation we did before. So we see we have to do the washer method because we've got that inside radius at a half and the outside radius up to one of those curves. For the first part, this bit here, it's going to be from here to here is the inside radius. From here to here is the outer radius. We see that the outer radius is with this root function. But over here it changes. From here to here is the inner radius. From here to here is the outer radius. So this outer radius changes. Now we're looking at the line. So we can write here for this first bit, we can just cut this here. Okay, we cut it in half. That left side part, inner radius is a half. And the outer radius is root x. Okay, because we're on the left side of the cut there. On the right side of the cut, we've got a different line at the top. That's this straight line at the top. So the inside radius is still a half. And the outer radius is now 2 minus x, because that top line changed. Before it was root x, now the top line is 2 minus x. So the radius changes, so we need to do that as a separate problem. Okay, good. Okay, any other questions? Okay, let's have a look at the last problem for today. Okay, number 5. We have y equals 2 root x minus 1, y equals x minus 1, about the line x equals minus 1. So now we're rotating around this new line, x equals minus 1. So let's sketch this. Okay, so 2 root x minus 1, that's going to look something like this. Okay, so it's just your normal root function, but shifted to the right by 1. And then x minus 1, that's going to look like this. There. Okay. Okay, so we've just sketched the 2 lines there. We know that this intersection point here is going to be 1. Right, because that's the x-intercept for the straight line. What about that other point over there? We need to find out what that is. So this point here, what is that? Okay, that's one of the intersection points. So we just make the two lines equal and we get what that point is. So we're going to have 2 root x minus 1 is equal to x minus 1. Solve for x and you end up with x equals 5. Okay, so we have our x values going from 1 up to the other intersection point here. That'll be 5. Okay, so here, as shaded in, that's our region of interest there. Okay, so that's the region. We've got the bounds for the region, but now we're rotating this around. X equals minus 1. So let's put in the axis of rotation. So that's going to be over here. That's our axis. So whatever region we have, we're going to rotate around this axis. Okay, so whatever that was over there, we flip around, and that's going to be our rotated shape. So we can just sketch that in here. Like that. Okay, and it's being rotated around there. So I've just flipped it over, but you get the idea. Whatever's on that side, we flip over and rotate around. So in terms of the volume, it's going to look something like this. Okay, it'll end up being something like that. Okay, so again, we need to use the washer method. Why? Because we see from the shape there, from the axis to the curve, we've got the inner radius and the outer radius. So here, we can fill that in. From the axis to this root function, that's going to be r in. From the axis to the line, that's going to be r out. Okay, so we've got the inside radius from the axis to the root. We've got the outer radius from the axis to the line. But now this has been flipped over. Now we're measuring it as x. X is now the horizontal distance we need to measure. Okay. So whatever our functions were, we need to solve them in terms of x. That's the horizontal distance. So the first function here was y equals 2 root x minus 1. We don't want y. Y is a vertical distance. We want x. That's the horizontal distance. So we're going to have y squared is 4x minus 1. So 1/4 y squared plus 1. That's x. Okay, so that's the horizontal distance for the root function. And for the other one, we have y equals x minus 1. So x equals y plus 1. So these are the two horizontal distances that we need to work with for r in and r out. Okay, so what's the distance going to be? For r in, the x value is from the y-axis to the curve. That's x, y-axis to the curve. But the axis of rotation is at x equals minus 1. We need to add 1 to the distance. So from the line x equals minus 1 to the y-axis, that's 1 plus the x distance from the y-axis to the curve. Same thing for r out. We need to add 1 because of that extra distance to the axis. So we end up with r out is equal to y plus 2, and r in, that's going to be 1/2 y squared plus 2. Everyone see how we got that? Anyone? No. Okay, this bit here. Let's put it rainbow. This bit here, this distance is x. Okay. from the y-axis to the curve is x. We know what x is, we just found it over here. Okay. But we also need to include this distance. The full distance is x, the distance from the axis to the curve, plus 1, because we still need to go to the axis, x equals minus 1. This distance is 1. So r out is the full distance. The full distance is the x value plus 1. So if the x value is y plus 1, then r out is y plus 2. We need to add 1 for that extra distance. So that's for the line. For the root function, x is 1/2 y squared plus 1. We need to add 1 because of this extra distance here, this bit here. So we add 1. So 1 plus x, that's r in. And then for the top, 1 plus x, that's r out. We need to add that little bit in. Okay, that gives us r in and r out. Okay, so let's find the volume. So the volume is going to be the integral from 0 to 4. Okay, now we're going along. Yes? Oh, sorry, yeah, that's supposed to be 1/4. Yeah, I had it correct over there. Yeah, so 1/4. Okay, so r in, 1/4, same as what we had there. Okay, so we have pi. Now we need r out squared minus r in squared. So r out squared, that's y plus 2 squared. Okay, please don't forget to square your radii for this. Okay, minus r in squared, that's 1/4 y squared plus 2 squared again. dy. Okay, now we just need to expand the brackets and then solve as normal. So that's going to be pi integral from 0 to 4. The first one, that's going to be y squared plus 4y plus 4 minus. Okay, then we need to square the second bracket there. That will be 1/16 y to the 4 plus y squared plus 4. Okay. And then we can just take the minus sign inside and simplify. So this will be pi integral from 0 to 4, y squared plus 4y plus 4 minus 1/16 y to the 4 minus y squared minus 4. Okay, we've got a plus 4 and a minus 4, so they can go. And then we just integrate as normal. So that's going to be pi 1/3 y cubed plus 2y squared minus, that's going to be 16 times 5 from there. Okay, y to the 5 minus 1/3 y cubed from 0 to 4. Sorry. 0 to 4. Yeah. 0 to 4. Okay, the 0, that doesn't do anything. Yes? 4 from this intersection point that we found. Y equals 4. Yeah, x is 5. If x is 5, y is 4. Yeah, that was on the side working we did earlier. Yes? Sorry, the? I'm not following. Where? Which line? Y squared cancels. Yes, sorry. Yeah, that's a minus. Yeah, that goes. Yeah, that's right. Okay, yeah, so y squared minus the plus y squared, that cancels. Okay, so now we can put in the 4. So that will be pi 1/3 4 cubed minus 1/16 times 5, 4 to the 5, minus 1/3 4 cubed. Okay, and again, you have your calculators, so you can just put that in and simplify. Yeah. Yes? Sorry, the why? Oh, okay, no, I see. Yeah, that goes. Yeah, that all goes there. Yeah, so we're just left with that bit there. Okay. The? Oh, no, sorry, cancel that there. That was the 2y squared from there. Yeah. That's 4y squared. Okay. Anything else that's wrong before we move on? Sorry, one person, please. What is it? Okay, let's just do that again. So we have the volume is the integral from 0 to 4 pi. Okay, r out is y plus 2. Yeah. Okay, minus, and then r in, we had 1/4 y squared plus 2. Okay, dy. Okay, so this is going to be pi integral from 0 to 4 y squared plus 4y plus 4. Okay, everyone agree with that? Okay, minus. Okay, then this thing squared, that's going to be 1 over 16 y to the 4 plus y squared plus 4. All good? Okay. dy. Okay, things going to cancel. We've got y squared minus y squared. That goes. We've got a plus 4 and a minus 4. That goes. All good? Okay. So then we have pi integral from 0 to 4. 4y, that stays, minus 1 over 16 y to the 4. That stays, dy. Good? Okay. Then that will be pi. That will be 2y squared minus 1 over 16 times 5, y to the 5, 0 to 4. Is that good? Okay. And then pi, the 0 doesn't do anything, so it's going to be 2, 4 squared minus 1 over 16 times 5, 4 to the 5. Good? Okay, so we end up with that. Okay, thanks. Okay, any questions about the inside radius and the outside radius with that adding 1? Does everyone understand why we had to add 1? Okay, cool.